Today we're going to explore one of the most remarkable experimental discoveries in semiconductor physics, Leo Isaki's discovery of quantum tunneling in diodes. This case study perfectly illustrates the scientific method in action. In 1957, Leo Isaki was working at Sony Corporation in Japan, studying heavily doped semiconductor junctions. He was measuring the current voltage characteristics of PN diodes, expecting to see conventional behavior. But first, what exactly is a PN diode? Let me explain the fundamental physics. A PN diode consists of two semiconductor regions. The p-type region has an excess of positive charge carriers called holes. The n-type region has an excess of negative charge carriers, which are electrons. Where these two regions meet, we have what's called the junction. According to classical semiconductor theory, when you apply voltage to a diode, the current should follow a specific exponential relationship. This is described by the Shockley diode equation. The current I equals I0 times the quantity e to the qv over kt minus 1. Here q is the elementary charge, v is the applied voltage, k is Boltzmann's constant, and T is temperature. What does this equation actually predict about diode behavior? In forward bias, when you apply positive voltage to the P side, current increases exponentially with voltage. In reverse bias, when you apply negative voltage, you get only a very small leakage current. Here's what the expected classical IV curve looks like. Notice the exponential increase in forward bias and the flat negative current in reverse bias. This is what every physicist expected to see. Now let's look at what Esaki actually did in his laboratory. Esaki decided to use extremely heavily doped semiconductors, far more than what was typical at the time. The doping concentration was about 10 to the 19th to 10 to the 20 carriers per cc. He carefully measured the current voltage characteristics of these heavily doped PN junctions, taking data points across a range of applied voltages. When Esaki plotted his experimental data points, something extraordinary appeared. The curve did not match the classical prediction at all. Here are the actual experimental data points that Esaki measured. Notice something very strange happening in the forward bias region. The current first increases, then decreases, then increases again. What was this bizarre feature that appeared in the data? Let me highlight the anomalous region. In this region between the peak and the valley, as voltage increases, current actually decreases. This is called negative differential resistance, and it was completely unexpected. Why was this observation so shocking to the physics community? According to classical semiconductor physics, current should always increase monotonically with forward voltage. There's no mechanism in classical theory that would cause current to decrease. This negative resistance region seemed to violate our basic understanding of how electrical resistance works according to Ohm's law. Esaki proposed a radical explanation: quantum mechanical tunneling. But what exactly is quantum tunneling? In quantum mechanics, a particle like an electron can pass through an energy barrier that it classically shouldn't be able to cross. It's as if the electron can tunnel through a solid wall. Esaki developed a detailed quantum mechanical model to explain his observations. When you dope semiconductors extremely heavily, the depletion region at the junction becomes very narrow, typically only about 1 to 2 nanometers wide. At this narrow width, the probability of quantum tunneling becomes significant. Electrons can tunnel from the conduction band on one side directly to the valence band on the other side. The tunneling probability T is approximately e to the negative 2 kappa d, where d is the barrier width and kappa is related to the barrier height. Now here's the key question. How does quantum tunneling explain the negative resistance region? At low voltage, filled states on one side align with empty states on the other side. This is where tunneling current is maximum, corresponding to the peak in our IV curve. As voltage increases further, the energy bands shift and the overlap between filled and empty states decreases. This reduces the tunneling current, creating the negative resistance region. Let me show you the complete picture with all three regions explained. Region 1. Tunneling current dominates and increases with voltage. Region 2. Negative resistance as tunneling decreases. Region 3. Normal diffusion current takes over and increases exponentially. Science requires verification. How did Isaki verify his quantum tunneling hypothesis? Esaki measured the IV characteristics at different temperatures. Tunneling current should be relatively temperature independent, unlike thermal diffusion current. He varied the doping concentration and observed that the negative resistance region only appeared with sufficiently heavy doping, exactly as the tunneling model predicted. Additional experiments with magnetic fields provided further confirmation of the quantum mechanical nature of the current transport. This discovery beautifully illustrates the scientific method. Let me summarize the key steps. First, Esaki made extremely careful and precise experimental measurements of current versus voltage. Second, he systematically plotted his data points and looked for patterns and anomalies. Third, he identified the negative resistance region as something that couldn't be explained by classical semiconductor theory. Fourth, he proposed a new model based on quantum mechanical tunneling to explain the anomaly. Fifth, he made specific predictions based on his model and tested them through additional experiments. Finally, the discovery was verified by independent researchers around the world. What was the impact of Esaki's discovery? Esaki was awarded the Nobel Prize in Physics in 1973 for his discovery of tunneling in semiconductors. The tunnel diode became an important electronic component, especially useful in high-frequency applications. This work laid the foundation for many modern quantum devices, including resonant tunneling diodes and quantum cascade lasers. What can we learn from this case study? The first lesson is that anomalies in data are not problems to ignore, but opportunities for discovery. Esaki could easily have dismissed the negative resistance as measurement error or equipment malfunction. Instead, he took it seriously and investigated it systematically, leading to a Nobel Prize-winning discovery. The second lesson is don't be afraid to question established theory when data contradicts it. Classical semiconductor theory said negative resistance in this regime was impossible. But Esaki had the intellectual courage to propose that quantum mechanics was necessary to explain his observations. The third lesson is that precision in experimental measurements is absolutely critical. The negative resistance region was a relatively small effect. Without careful, precise measurements, it could have been missed entirely. This emphasizes the importance of proper instrument calibration, error analysis, and attention to experimental detail. Now let me give you a practical exercise you can try. If you have access to a tunnel diode and appropriate measurement equipment in your laboratory, measure the current voltage characteristics at room temperature. Take data points every 0.01 volts in the forward bias region. Plot your data carefully and identify the peak current, valley current, and the negative resistance region. Calculate the peak-to-valley current ratio. This is an important figure of merit for tunnel diodes. The peak-to-valley ratio equals I peak divided by I valley. For good tunnel diodes, this ratio is typically between 5 and 15. For more advanced students, you can analyze the energy band diagrams quantitatively. The tunnel current density can be calculated from quantum mechanics. J equals Qm star over 2 pi squared h bar cubed times the integral of T of E times the quantity F1 of E minus F2 of EdE. Here, T of E is the tunneling probability, and F1 and F2 are the Fermi functions. This integral can be evaluated numerically for specific device parameters to predict the entire IV characteristic. You can then compare your experimental IV curve to the theoretical predictions and quantify any deviations. The story doesn't end with Esaki. Let me briefly mention modern extensions of this work. Resonant tunneling diodes use quantum wells to create multiple negative resistance regions, enabling even more sophisticated device operation. The physics of quantum tunneling discovered by Esaki led directly to the invention of the scanning tunneling microscope, which won another Nobel Prize. Today, controlled quantum tunneling is being explored for quantum computing applications and other quantum technologies. Let me summarize the key points about the scientific discovery process illustrated by this case study. First, make precise and careful experimental measurements. Quality data is the foundation of discovery. Second, plot and visualize your data systematically. Patterns and anomalies become obvious when properly graphed. Third, actively look for data that doesn't fit established theoretical models. These are your opportunities. Fourth, propose explanations for anomalies and test them rigorously through additional experiments. Fifth, Be intellectually prepared to invoke new physics when classical explanations fail. Finally, always verify through independent measurements and alternative experimental methods. Leo Isaki's discovery of quantum tunneling in heavily doped semiconductors is a perfect example of how experimental physics should be done. It demonstrates that careful, precise experimental measurement must always trump theoretical prejudice. It proves that anomalies in data are not experimental nuisances to be explained away, but windows into new physics. And it shows that young researchers, when they trust their measurements and think independently, can make revolutionary discoveries.